Hello, this is Mr. Craig, and here's the second titration question that I want to work on for the 2022 day before the AP exam. Hope this information helps. All right, so the question says potassium sorbate, which is K6H7O2, has a molar mass of 150 grams per mole, is commonly added to diet soft drinks as a preservative. A stock solution of the potassium sorbate of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with a 1.25 molar hydrochloric acid using both an indicator and a pH meter. The value of the Ka for the sorbic acid is 1.7 times 10 to the negative 5. A asks you to write the net ionic equation for the reaction between the potassium sorbate and the hydrochloric acid. Remember that when we talk about net ionic equations, we only involve those ions that are involved in making something or things that are changing. So we know that potassium sorbate is a strong salt because we have potassium. The sorbate we don't know that much about, but again, anything with group 1A metal is going to be strong, so that means it'll break apart completely. Hydrochloric acid is also a strong. We know that to be one of our 6 strong acids. Remember, it's hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, chloric or perchloric acid are the other strong acids. So make sure you remember your strong acids. They dissociate completely. Now, this is a double replacement reaction, so I did write the products here. But we have the formation of a weak acid. This is sorbic acid. Again, we know it's weak because we have a Ka value of 1.7 times 10 to the negative 5. We know potassium chloride is very soluble. Anything, again, with a group 1A metal will dissociate and not form a new thing. So the net ionic equation is just your sorbate ion plus the hydrogen making sorbic acid. Do that, give yourself a point. Part B says a total of 29.95 milliliters of the 1.25 molar hydrochloric acid is required to reach the equivalence point. Again, equivalence point means that the number of moles of the acid are equal to the moles of the base. So in this case, we're going to treat this potassium sorbate, this, where is it? Right here, this C6H7O2 as the base, because again, it needs a hydrogen to jump on it to make it an acid. So when if we were to put this into water, it would rip a hydrogen off, leaving hydroxide and this sorbic acid. Now, nowhere in this question does it ask you to do that, but you have to realize that this is the acid, this is its conjugate, which means that if this is an acid, this is a base on the other side. So remember the MAVA equals MBVB equation, and again, this is only for at the equivalence point when the number of moles of acid equal to moles of the base. So we know we have 1.25 molar of hydrochloric, it's given. 29.95 milliliters, given. 45 milliliters, that was given right up here at the very beginning. So make sure that we're reading the information so we know how much we actually have. So that means that the potassium sorbate had to been at a 0.832 molar concentration. And you can see how you earn your points. But again, if you show this MAVA, you get both points. So you don't necessarily have to go through and find out how many moles of hydrochloric you have. But again, if you wish to, there's more than one way to solve these equations. Part C says the pH at the equivalence point of the titration is measured to be 2.54. Which of the following indicators would be the best choice for determining the endpoint of a titration? And then justify your answer. Again, when you're asked or you're given a list of indicators, you want to find the indicator that is closest to this pH. So the pH at the equivalence point. That is what we're focusing on right there. Okay, now 5.0 might be a good choice because it might alert you that you're approaching 2.54, but keep in mind that if you are getting or have an indicator that's close to 2.0, that you will start to see remnants of this indicator appear and then disappear. I did link in the student calendar some example titrations. like probably the most famous one, the one that we did in class as well with the phenolphthalein, that it's that pink color starts to show, then it goes clear, starts to show for longer, goes clear, etc., until we hit the equivalence point, then it stays permanent pink. So if you need to watch that video, I do have a link in the calendar that does say that it's a titration demo. So our best choice should be the thymol blue. And I put on here, we need an indicator that will let us know when we are approaching the equivalence point, not after we've passed the equivalence point. So if we have an indicator at 5.0, we'll never know when we get to 2.54. At least once we get to 2.54, that thymol blue, as the case of the phenolphthalein, will actually get darker, stay longer for a much longer period of time. So not a great question because, again, our pH is 2.54 and our indicator is appearing well after because we're starting with a base and we're titrating it with an acid. But, again, we got to work with what we've got, and this is what we've got, sadly. All right, the next part says calculate the pH at the half equivalence point. Now, again, at the very beginning of the question, and I cut it out again, it tells us that we have a Ka value for the sorbic acid to be 1.7 times 10 to the negative 5. This was given to us at the beginning. Keep in mind that we know that at the half equivalence point, because that's what we're looking for, at the half equivalence point, that the pH is equal to the pKa. What does that P mean? That's a negative log function. Okay, so also at this half equivalence point, the question doesn't ask it yet, but we know that the weak acid is equal to the anion, or the hydrogens that have been ripped off of this weak acid, and that's how much of that remains. Now again, this is if we start off with a weak acid. We are not. We're starting off with a base here, but it's asking us a question about this. So if we know the Ka is 1.7 times 10 to the negative 5, take the negative pKa, or I'm sorry, the pKa is a negative log of 1.7 times 10 to the negative 5, 4.77. That is our pH at the half equivalence point for this question. Oh boy, this graph is, or this titration curve is beyond ugly. I'm not very impressed with if we actually have a titration curve that looks like this. If we were to talk about the buffer capacity, remember when we titrate an acid with a base or a base with an acid, that the pH doesn't change by a whole lot. Well, this whole titration curve is just absolutely bonkers. They gave us this point here. If you look carefully on the original sheet, you'll see that that dot is right there. They also gave us this dot, indicating that that's the equivalence point. So it says on here the initial pH, boom, right there, and the equivalence point are plotted on the graph below. Accurately sketch the titration curve on the graph below. Mark the position of the half equivalence point on the curve with an X. I actually marked the point. So we know that the equivalence point is at 29.95 milliliters. How do we know that? It was told to us in part B for the hydrochloric acid. We know that the half equivalence point pH is 4.77. We just found that in the previous question. So if I move to these 2 points here, here's my point for the half equivalence point, somewhere in that ballpark. Just make sure you mark it with an X. So again, whenever we titrate, the pH starts to drop immediately, and then it'll quote unquote level off. So really, from here to here, technically would be the buffer capacity, which again, there's no way that College Board could ask a question about where is the buffer capacity of something like this because you are creating this graph. Also realize that once the buffer capacity has been exceeded, we will hit the equivalence point and then that pH will continue. I did finish this. It didn't ask you to finish it, but hydrochloric acid should finish well below 2. But again, the points that you get for this is that you get 1 point for the, here, let me just go to it. So there's their answer. It says you get 1 point for the half equivalence point consistent with the answer in part D. So if you said 4.77, there you go. You get 1 point for the curve that levels off to the relatively horizontal. Again, it's not horizontal. Mine is more horizontal than theirs. And again, I really hate this curve. That's my editor's note. And then you get 1 point for a relatively steep negative slope through the equivalence point, which they're showing here. And we know that it's going to do something like that because once we hit the equivalence point, all of the base is gone. We only have the acid, so there it takes off and goes to a pH below 2. Well, what really sucks about this is a pH that's between 2 and 3, so there's really not a whole lot that it's going to do. Again, not a fan of this titration curve, but I will tell you, this question was asked in 2015. So within the last 10 years, so College Board is still throwing out some crazy situations, so be ready. And again, this is a base being titrated with a strong acid. All right. This last one, a fun one, says the pH of the soft drink is 3.37 after the addition of the potassium sorbate. Which species, the sorbic acid or the sorbate ion, has a higher concentration in the soft drink? Justify your answer. So remember, if it says justify, you may use words, you can write sentences, or you can do a calculation. I think I did both. So I know the Henderson-Hasselbalch equation looks like this. So I did pH equals pKa. We found that to be 4.77. We know the pH is 3.37, which is below the half equivalence point. So I just did some cursory things here saying that the log of 1 we know is equal to 0. So if you plug that into the equation, pH would be equal to pKa. Doesn't change anything. That if we have a log value greater than 1, that gives me a positive value. So a positive to a positive would mean the pH would need to be higher than 4.76 or 77, whatever the number is. However, if I have a log value that is less than 1, then it gives me a negative value. Again, I'm just picking arbitrary values here. So I don't want you to go, where did you get log of 2? Where did you get log of 0.2? I'm just trying to get a number that's bigger than 1 or smaller than 1, so I can get a sign, because I know that the log of 1 is 0, that the log of a number greater than 1 is a positive number, the log of some number below 1 is a negative value. So if we want to decrease the pH from 4.76 when it is a log of 1 at the equivalence point, or sorry, half equivalence point, that we're looking for a negative, or we're looking for a value that's less than 1. For it to be less than 1, that means that this A minus must be smaller than the HA. So the HA has to be greater. So I put on here for the pH to decrease from 4.76 or 77, whatever we found it to be, the log of the anion divided by the HA, the acid, the weak acid, the sorbic acid, must be below the value of 1.0. Therefore, the sorbic acid must have a higher concentration than the sorbic ion. So did I answer the question? Which one has a higher concentration? I did. So good job for me. I ATFQ'd it. All right, and then here is what they gave. So you get 1 point for identifying the correct species and making a comparison involving the pH with or without a calculation. And I didn't do a calculation. I just discussed the values. So they did their thing, and again, you can do whatever you need to do to solve for it. Again, I like Henderson-Hasselbalch. I'm not saying you need to learn Henderson-Hasselbalch to answer this question, but it is nice. They also have on here for the concentrations of the sorbic acid and the sorbate ion are equal to half equivalence point. Said that. Very good. And the pH is 3.37 is lower than that of the half equivalence point, so the protonated form of the that doesn't really give us a great answer. But again, I like this. Okay. Hope this video has been helpful. A little below 15 minutes. All right.